Hey folks, I want to go over the answers to part 1 of our solar system and astronomy test. So let's just jump right into it. Which evidence best supports the Big Bang theory? So if you remember from our notes, we were talking about that the universe all started at a very, very small point with all the matter and energy and then expanded very quickly. And so there is some evidence that shows that actually happened. And some of the evidence is the fact that we have a redshift. We talked about radiation that's still everywhere that we can see. So let's try to find that in our answers. The rate of the rotation of the sun. Well, rotation doesn't have much to do with just the entire universe. The existence of cosmic background radiation. Number 2. Now that seems to be pretty close. Uniform radioactive decay of uranium-238. Well, that's just one element. Separation of Earth's interior into different layers. Well, that's just our Earth. But if we think about the entire universe, it's going to go back to number 2. So the existence of cosmic background radiation. All right. Let's go to number 2 here. Number 2 was a question that said, which process combines lighter elements into heavier elements and produces energy within the sun and other stars? We talked about this when we bring lighter elements, you fuse them together, and they become heavier elements. And so if you're fusing, you're bringing it together, that would be fusion. So number 1. Insulation talks about how much energy is coming to the Earth. Conduction, we'll get into that when we start talking about weather. And radioactive decay, well, that's going to be back with the unit on Earth history. So number 2 was 1. Number 3, which star has a surface temperature most similar to the surface temperature of Alpha Centauri? And so here we have to take a look at our Earth science reference table. So here we go. We're going to try to find Alpha Centauri. Well, there's Alpha Centauri. What we need to do is understand what the x-axis and the y-axis represent. Now, the x-axis is temperature, and the y-axis is luminosity, which means just how much energy is emitted from that star. We're really focused on the temperature here because that's what the question asked. So they said, all right, there's Alpha Centauri. So we can kind of come down. We can see it's around, 5,500 degrees Kelvin. Now the question is, which star from the choices they gave us is most close to Alpha Centauri? So we're going to be looking left and right to see which of those options is most close. Well, one of the options was Polaris. And so I can go up to Polaris, and Polaris looks like it's pretty much in line with Alpha Centauri if I'm thinking left-right. We have Betelgeuse, which is over here, and that looks like it's a little further to the right. We have Procyon b, and that's down here, and it looks a little over to the left there, and Sirius, which is, where can we find that? Again, a little over to the left. So the one that looks to be most lined up, all right, at the same temperature down here is going to be Polaris, and therefore our answer for 3 is number 1. And that came from page 15 in our Earth Science reference tables. Let's go to question 4. Scientists infer that the universe began approximately, and this is directly from our notes, this is approximately 13.7 billion years ago. Now, question number 5. We have a little diagram here, so let's read some information. The diagram below represents the spectral lines from the light of an element in a laboratory on Earth. So we know that a certain element emits lines 1, 2, 3, 4, 5 in this pattern. Now the question is, which diagram below best represents the pattern of spectral lines from the same element, all right, the same element here, when it was observed by the Edwin Hubble in the light of one of the distant galaxies? Now, you don't need to know what Edwin Hubble is. It's just a type of telescope. So you're looking out in outer space. We did talk about that all galaxies are moving away from each other because the universe is expanding. And when things move away from each other, their spectral lines get shifted towards the red end of the light spectrum. Well, let's look at our original diagram. The red end is over here on the right-hand side. So we should see the same pattern, 2 close to each other and 3 also close to each other but separate a little bit more. And we want to see which option shows them a shifting down to this end of our red spectrum. Well, it looks like this is not the same shape. These 2 lines are too far apart. This is the same, but it's moved down to the violet. That won't help. These two are a little closer than the original ones. So number 3. These are all 3 lines are the same distance from each other, and so is that, and they're all shifted down close to the red. So notice the 3 are here, and now they're a little close to the red. So number 3 is our correct answer. Question number 6. Which event occurred approximately 4.6 billion years ago? Well, the evolution of Earth's earliest fish, evolution of the stromatolites, formation of the oldest known Earth rocks, or formation of Earth and our solar system. Well, this is also directly from our notes, and we can see, well, we can also take a look at, I think it was page 8 and 9, the Earth history, all right? So if we actually look on here, we have millions of years, and we can see that the estimated time of origin of Earth and solar system is 4,600 million years, which is 4.6 billion years. You could have looked on the sheet. You didn't have to because the data was right in our notes. That was when the Earth formed around with our solar system. Question 7. Which 2 characteristics do all Jovian planets have in common? Well, we have that in our notes. And something that they're all similar with is that they are very big. So their diameters, the distance from one side of the circle, if you draw a line through the next side, is going to be the diameter. But they also have something that has low density. So you can actually take a look at that here on page 15. So this bottom section here. Well, Jupiter, Saturn, Uranus, and Neptune. All 4 of these are Jovian planets. And so we could go over here. We could see that their diameters, 142,000, 120,000, 51, 49. If you look at all the planets above it, none of them are even coming close to, say, 51,000 or 49,000. The biggest is 12,000, which is going to be Earth. So their diameters are bigger, but look at the densities. These bottom 4 numbers are densities. 1.3, 0.7, 1.3, and 1.8. None of them come close to the densities of the other planets. They're in the 5s and the 3. So the densities are lower and the diameters are bigger. For that, we can go take a look at our answer for question 7, is that they have large diameters and low densities. So question 7, the answer is 3. Now question number 8 had to deal with planets moving around. So which planet takes more time to complete one rotation on its axis than to complete one revolution around the sun? So you're going to have to go back to page 15 of your Earth Science reference page. So let's take a look at that. Well, right here we have our revolution, and right here we have our rotation. And what they're asking us is which planet has more time for rotation compared to revolution. So we're looking for a number that's in this column that's bigger than the revolution. And so our options are Mercury. Well, Mercury's rotation is 59, but 59 is smaller than 88. Venus. Well, Venus is 243 days, and the revolution is 224 days. So there you go. Rotation is bigger for Venus compared to its revolution. Let's just check Mars. It's another option. 24 hours compared to 687 days. Obviously, that's smaller. And our last option is Jupiter, 9 hours to 11 years. Well, it's definitely Venus because its rotation, as they said, is bigger than its revolution, which is 224. So if we go back to question number 8, Venus, number 2 is our answer. Now, number 9, during which northern hemisphere season is the Earth closest to the sun? So this trips up a lot of people because they still think that we're closer to the sun in the summer, and that's what makes us have summer. But you now know that it's because the angle of the Earth's axis is tilted towards the sun. So it doesn't have to do with distance. So it's actually opposite. We are closer to the sun during winter when it's winter in the northern hemisphere. So number 9 is 4. Number 10. What causes many surface winds to deflect to the right in the northern hemisphere? So this was actually a piece of evidence that proves that the Earth is rotating on its axis. And so this is actually the name of it is the Coriolis effect. And so the Coriolis effect is actually the rotation of Earth on its axis. So we had that from our notes. Question number 11. Evidence that the Earth revolves around the sun is provided by, well, how do we know that the Earth is actually moving around the sun? Well, what evidence do we have? Well, the apparent rising and setting of the sun during one day. Well, that's not revolution, that's rotation, the Earth spinning. Apparent rising and setting of Polaris during one day. Again, that's rotation on its axis. Seasonal changes in the apparent position of constellations. Well, we do have seasons because our Earth's axis is tilted and we're not in the same position, so we are going around the sun. Number 4, hourly changes in the apparent direction of the swing of the Foucault pendulum. Remember, we said Foucault pendulum was because of rotation. So number 3 is our correct answer. And again, we're not going to see the same stars throughout the year because at nighttime, we're going to be looking out to different places in the solar system and the universe as well, because we're moving around the sun. So number 11, that's going to be 3. 12, they gave us a picture. And these pictures are really nice to give us a perspective. Now, the diagram below represents Earth in space on the first day of a season. Now, let's take a look at this. It looks like Earth's axis is tilting away from the sun's rays. So, which season is beginning in New York State on the day represented in the diagram? Well, we did have our diagram inside of our notes, and it shows that when the Earth's axis is tilting away from the sun's rays, that season in New York State is going to be the winter. That one came directly from our notes. So question 12 is number 1. Question 13, again, they gave us a diagram, but they also gave us some options here for our questions. Now, this diagram represents the horizon and the sun's apparent paths A, B, and C on different dates, like we're in New York State. So here's our horizon. They labeled it for us. And remember, the sun rises in the east and then sets in the west. And there are 3 times when we can see this. Now, the question was, what are those dates? So the sun is higher in the sky during A. For B, it's kind of in the middle. And for C, it's lower in the sky. So going back to our notes, we're talking about the altitude. So how high up is the sun? Well, the sun is the highest on the sun is the highest on June 21st, and that's going to be summer. And the sun is the lowest on December 21st, and that's going to be the winter. And so sometime in between has to be either September or March. So let's try to find where A is June 21st, B is March 21st or September 21st, and C is December 21st. So I'm going to look at A. So December, nope. December, March, nope. Looks like question or option 4 has June. Let's make sure B is correct. March or September, March matches, and C is December 21st. So it looks like number 4 for 13 matches up, knowing that the altitude of the sun changes throughout the year. So we had a kind of similar diagram here. So questions 14, 15, and 16 use this. And once again, this is our horizon. Pretend that we're in Jamestown, New York, which is west of us. It's a little southwest. It's just north of the Pennsylvania border. And there's these different paths. So June 21st is path A, path B, path C, and path D is December 21st. Now, we don't know the dates of B and C here. And they give us a little circle here with an S saying this is the sun. Now, we also know that this is solar noon. Now, remember, solar noon is when the sun has been up for half of the time, and then the other half, it'll be setting. So it's halfway through when we see the sun. Let's take a look at our questions here. So question 14. The greatest duration of insolation in Jamestown occurs when the sun appears to travel along which path? A, B, C, or D? Well, you have to know what insolation is, and that's the amount of energy that comes from the sun. So when is the sun out the longest? Well, that's going to be the path that is the furthest, the biggest path, or the biggest arc right here, and that is path A on June 21st. So 14 is number 1. 15. At what time of day is the sun at position S? So here we have position S. All right, well, this is sometime between June and December. So it might be sometime, maybe we could say it might be in May or April or after June. It might be sometime in like the fall. All right, now this is solar noon, and this would be early morning in the sunrise. So this might be around 6 a.m., and this might be around 12 o'clock. So somewhere between 6 a.m. and 12 noon. And so if you look at our options, 6 a.m., well, that's too early. 9 a.m. seems optional. 3 p.m. and 6 p.m. Well, 3 p.m. and 6 p.m. would be on this side of the arcs. 6 p.m. would be down here. It looks like 9 a.m. Would be our best option, so number 2. Number 16, last question for this diagram. When the sun travels through path D, what orbital position is Earth closest? Well, let's look at path D. Well, here's path D, December 21st. If you looked at that diagram inside of our notes, we could see that that is December 21st, and that's when the sun is the closest to the Earth. Well, that position itself is going to be very close to the Earth, and the position is actually called perihelion. So Earth is in winter position during perihelion, so it's actually closest. So 16 is number 1. All right, moving on, number 17 here. Which motion causes the moon to show phases when viewed from Earth? Well, why do we see different portions of the lit up side of the moon? Well, it's because the moon is actually moving around us. So the rotation of Earth on axis, no, that's really going to give us day and night. The revolution of the moon around Earth, well, yeah, the moon is moving around Earth. So this seems like our best option. The rotation of sun on its axis, that's going to have nothing to do with the moon phases. The revolution of sun around the moon, well, we all know the sun does not go around the moon. So B is our best option for 17. Number 18 here. A student drew the phase of the moon observed from one location on the Earth on each of the dates shown. So May 4th, we have our crescent. May 8th, we have our quarter moon. May 12th, we have our waxing gibbous. May 16th, we have our full moon. May 20th, we have our waning, meaning it's getting smaller gibbous. Remember, gibbous means that we're seeing more than half of the lit up side. So it looks like they're starting to chip off a little bit on our right-hand side. They're asking us, what's the moon going to look like to us on Earth on May 24th? So we're going to have to take off a little more of this, and that's going to match up with option D here. So again, we're just notching off a little bit more on the right-hand side. Eventually, it's going to get to D on May 24th. So here's question number 19. Again, they give us a diagram. Now, the diagram shows the relative position of the Earth, Moon, and Sun for a 1-month period. Now, what's happening is we're looking actually down, say, on the North Pole, and that's perspective that we have. The question for us is, which diagram best represents the appearance of the moon at position P when viewed from Earth? So here's position P, and now it's a little more difficult, obviously, when you are taking a test physically or online. It's easier when it's physical. So I'm going to do this, and we practice this a bit, but it's going to be much easier on the regions when you have a physical piece of paper. So you're going to draw a line from this position straight to Earth, and we're going to label this left and right. And this line right here, we're going to imagine this is a half of the moon that we're seeing. This is the other half. And it looks like that some of the shaded part has pushed over into the left-hand side. And we're only going to have a small portion of the moon that we see on the left-hand side. Now, the whole right-hand side is going to be dark, and we're only going to have a small sliver over here on the right-hand side. Because remember, if I drew a line here, we can't see anything back here. We can only see stuff in the front part of the moon that's looking at us. So where do we have a sliver on the left-hand side? Well, if we look at our options here, option A is the best. It looks like some of the shadow has creeped over the left side, so A will be the best. All right, moving on to number 20. Okay, so we have a diagram here. This is the Earth's position going around the sun, and this other orbital path is a comet. Now, the diagram shows Earth's orbit and a partial orbit of a comet on the same plane around the sun. Now, remember, this is not drawn to scale. The Earth is much smaller than the sun, and it's also much further away. Now, compared to Earth's orbit, the comet's orbit has, well, the comet's orbit looks like it's shrunk just a little bit. And remember, if we have a circle, all right, its eccentricity is equal to 0. But if you have a flat line or you have a very narrow circle, it's getting closer to the number 1. So that would be more eccentricity. And so if we look at this, compared to the Earth's orbit, the comet orbit, well, it's squished, so it's getting closer to 1, so it has more eccentricity. All right, so it's going from 0 to 1. Remember, we had some examples inside of our notes, and this is actually labeled inside of our notes that a circle is eccentricity of 0, and a straight line or a very flat ellipse is 1. 22, it said, according to the Earth science tables, which planet has the most eccentric orbit? And so they gave us some options. So let's go to that. So here we go. We're looking for eccentricity of orbit. And so we have 0.206, 0.007, all some small numbers. So we're looking here. It looks like Mercury has the largest one. Is that an option that we have on our question? Well, it looks like Pluto, Mars, Venus, and Saturn. So Mercury's not an option there. Now, we can automatically knock off A because we know that Pluto is not a planet. Now, let's just check. Mars, Venus, or Saturn? So Mars. Well, we're going to go Mars and go over to our eccentricity is 0.093. We have Venus, 0.007, so it looks like Mars is still winning against Venus. And how about Saturn? Saturn is 0.054. Well, Mars is still bigger than Venus and also Saturn, so it looks like Mars is the correct answer. So 21 is B. 22. The Coriolis effect provides evidence that Earth, again, this is directly from our notes, we had reasons or evidence for rotation and revolution. And which one is it? Well, Coriolis provides that the Earth is actually rotating on its axis. So winds would just go straight, but they are bent either to the left or to the right, depending on the hemisphere that you're in. We know we're in the northern hemisphere, so it gets bent towards the right. Here's question 23. Now, according to the Earth science reference tables, which orbital path model correctly shows the relative positions of the sun and its 4 nearest planets? So they're really asking us which one shows the correct order of the planets going around the sun. Well, you don't need to memorize the order. All we need to do is look in here. So we have the sun, then it goes Mercury, Venus, Earth, and Mars. So which one shows that correct order? Mercury, Venus, Earth, or Mars? Well, here we are. So option C, Mercury, Venus, Earth, and Mars. And Mars is the furthest. Mercury is the middle one, or I'm sorry, the closest one. So C was our correct answer for question number 23. Again, that's page 15 of our Earth science reference tables. The second last question. So here's a diagram, and it represents Earth. So it's kind of the size of Earth. The question is, which diagram best represents Mars drawn to the same scale? So if you look to your page 15 on the Earth science reference table, you will notice that Mars is not the same size as Earth. So let's go here. So here we go. Let's take a look at Earth and Mars. They're right next to each other. And if we look at the diameter, now remember diameter is a measure from one side straight across to the other side. All right? So Earth's diameter is 12,756 kilometers. Now, it looks like Mars's diameter is 6,794. So it's almost about half the size of it. So it's a bit smaller than Earth. So Earth and Mars, if we compare those. So now we have to try to figure out which one shows the same scale. So obviously, A is like much smaller. I would say it's even less than half of that. C is the exact same size. D does not look like it's half. B is our choice right here. It's the correct one because B is pretty much half the same size of this. It might go a little over, but remember, it was not 6,000, it was 6,700. So B is our correct answer for 24. Now the last question for part 1 for our test. A comparison of the age of Earth obtained from radioactive dating And the age of the universe, based on galactic Doppler shifts, suggests that. All right, so what are they really saying? All right, age of the Earth, okay, and then age of the universe. So which one? Well, remember, Earth is 4.6 billion years, and the universe is 13.7 billion. So which one's older? Well, the universe. So that means the universe had to form first, and then the Earth formed after that. So a long, long time ago, the universe came about. Earth is about the same age of the universe? No. You could look right in your notes. 4.6 is not the same as 13.7. The solar system and Earth formed billions of years after the universe began. Well, that makes sense. The universe started 13.7, and then 4.6 billion years ago, we had the Earth. So that's a good option. Number C, or letter C, the two dating methods contradict each other. No, it's the same method. That's okay. The universe is much younger than Earth. How can 13.7 be younger than 14.6? All right, so B is our correct answer. So that is our answer key for part 1 for our test. We will have part 2 coming up. Take a look for that and try to earn some points back. Good luck, folks.